So today, with David, we're going to talk to you about how to transfer hyperscale data centers underground. And we need to place these underground structures in the heart of our cities. We need to be able to sell the waste heat on one hand, but we must respect also the major regulatory and social hurdles that your industry now faces. There's a huge pushback by local communities on these projects, and generally the projects are significantly delayed. So there's an acute awareness of the timeline, the urgency in the timelines. I just want to briefly say, you're probably very much aware of what's happening in the European level with the Energy Efficiency Directive, but Germany's got its own laws coming out, Energy Efficiency Act. France has come up with the Climate Energy Act and the Climate and Resilience Act, which basically limits the surface of land available to industry. And Switzerland has come up with the Federal Act on Spatial Planning and the CO2 Act. These are all major game-changing legal frameworks that we now have to work with. These acts have created land scarcity. It's an artificial creation. Basically, they're saying you cannot now build out your infrastructure without any limitation on use of land. And so now you have competition between the different stakeholders of industry against data centers. You've got a big problem with landmark visibility. People do not accept anymore to have big cubes on the landscape. And there's in the back of the mind, there's what happens when the data center guys leave. Will they leave all these empty buildings to rust? And then, of course, subject to many talks during this OCP summit, restrictions on energy availability and the major issue of wasting energy. A short video. Just to set the scene on visibility. I don't know if it...
No sound.
No?
Yes.
There's no sound?
Yes. I can just add. So the Microsoft evaluated that they should be in harmony with nature and with the people. So not take the land, but give the land. Not take the water, but give the water. And not take the energy, but give the energy. So this is the approach which is shown here. The idea is that it's already evaluated and delivered that message, and we're answering on that, how to handle that.
It was a very interesting talk by Christian Beladi of Microsoft. Then there's the problem, you've identified your data center location, and now you go forward. Then you think, oh, it'd be a good idea to also use the heat. Generally, the data centers are too far from the people who will actually buy the heat. You're looking for low land costs. You're looking for people who are willing to sell you the land. And generally, you're basically too far. So these projects never work really economically. So the path forward is to go underground. Plenty of land used for parking lots, industrial estates, where you can actually locate a data center, 50 megawatts, 160 megawatts, place it in the heart of the cities. One of the issues that we have with the aspect of fire, and I just want to show you what underground structures allow, which is basically oxygen reduction. So the short video just to show what happens when you walk into a low oxygen environment. You can't. Nothing ignites. This type of solution is very costly on the surface, very cheap underground. We talk about underground, so we must talk geology. It's something that generally hyperscalers don't look at, and should now become an element of their decision making. I've got a map of Marseille here, and you start looking at the geology. And where you see it's pink, that's where the geology is interesting, because these structures, the cost of these underground structures are heavily dependent on what type of geology you have. So you must start looking at where you can have good geology and then identify where you can put your data center. What we're looking for: rock impermeability, proximity to the surface. You don't want rock at 500 meters depth. You want rock layer thickness sufficient to house the underground structure, and of course you must be outside of flood affected areas. What does this imply? It means geology is a regional phenomenon. That means that certain cities, you cannot go ahead with an underground structure. I mean, Amsterdam is just impossible. It's just ground conditions are not favorable. Marseille, plenty of locations. So you can have London, Frankfurt, Paris, Dublin. These are all good places with good geologies. And what the challenge is to get the cost down. And so by standardizing underground structures, choosing the correct geology, then you get really interesting numbers, 335 euros per IT kilowatt, which is basically a third of the building on the surface. Remember, you don't need an architect for this. No preliminary studies that last years. You do your public inquiry. No oppositions, nothing to see. So you're cutting out years and years of studies. And then we're talking about sustainability. So what's the carbon footprint? Tunneling is a bit peculiar because you have to take also into account spoil, the carbon generated through disposal of soil or a spoil. And it's a bit peculiar because the designed life is 100 years, which is absolutely not the case for surface structure. So then you say, okay, at what point does the carbon footprint become interesting? Well, it actually becomes interesting from the start, because the actual embodied carbon is much less than a surface building. Why? It sounds a bit counterintuitive. It's because when you go sufficiently deep, it's the rock that supplies your structural members. It's not the concrete. It's not the 30 centimeters of concrete we put around the ring that's going to hold the structure. It's just there to protect the rock. So you're basically having very, very low carbon emission for every cubic of usable space. So we did a comparison with a warehouse. Warehouses have less carbon footprint than a data center, but we couldn't find any numbers on data centers. So, and we compare this, and we are 25% lower on carbon emission at construction time. But then things get better because we're using much less energy underground. And then when the second time comes around to demolish the old building and create a new building, then we get ridiculous figures, because we go up to 71% saving on carbon over the 100-year life cycle. So we have to have that in mind. You've got 25% immediate, but actually the long term is colossal. And then another question is often asked is about underground real estate. Well, this underground, to whom it belongs? Well, it depends on the country. The UK has defined a depth. In Switzerland, it's a relative depth. It's the depth at which it is still useful to you. In France, it's to the center of the earth. Of course, some things are excluded, like oil, gold. But as long as you're not sort of in the mining business, it's yours. You can actually create right-of-ways underground, and so you can sell your underground space independently of your land. You can continue to use your land for your current business and sell the right-of-way to a third party. And that third party then can resell that right-of-way to whoever he wants. So you get a total disconnect between the landowner and the right-of-way owner. The cost of the right-of-way is around 10 to 20% that of the surface. So if you've got land at 300 euros a square meter, well, you're going to pay only 30 euros a square meter. It changes, you cease to invest in real estate and you start putting that money into the data center itself. Quirk of the legal system or the tax system, there's no yearly taxes on infrastructure because a cavern is not a building. It's classified as a bridge and you don't have yearly taxes on it. So don't know how long that will last, but for the moment, no taxes on it. And just to give an overview, you've got on the left side a typical site installation inside a town. You've got the construction sequences in the middle, photos, and at the right you have what it looks like when it's finished. It's a clean structure. It's not like your usual cave that you store your wine in or whatever. It is very clean and dry. David?
Thank you, Andrew. Our task was to create a design which will sustainable. It means that we build at once, but we are ready for the next challenges, for the shifting from one solution to other. And in this case, you see that our big power is under surface. All the infrastructure is under surface, and only the heat rejection unit, in case when we don't have option, is placed on existing buildings, on the roof of existing buildings. And also was a challenge to find a solution which will allow us to reduce the noise level, to reduce the footprint, but we handle that. And again, if we need to make heat rejection, usually we use district heating network, and if we need during the summertime, this district heating becomes the district cooling network. So we can transport that heat far away from our city center and cool that in other areas. So it's a flexibility. So when we talk about flexibility, it starts from the rack level. So we choose the dense solution without raised floor, without ceiling, without hot and cold aisles. It's a door heat exchanger. So it's everywhere is a cool environment. And the temperatures which we use at the peak times, it's 34 degrees inlet water and outlet 44. And the flow rate per rack is 20 liters per minute. When we shift for the liquid cooling, we have the same flow rate, but in serial connection, we connect liquid cooling, and we can achieve 70 degrees with certain technology of on-chip cooling, and 36 kilowatt now is cooled by on-chip, direct-to-chip. So overall, we have 50 kilowatt per rack, but the same flow rate, so the same facility, tubing design, same pumps, and etc. And now when we will talk about the module, In each model, we will have 75 racks, which represent from 1 megawatt to almost 4 megawatt, but the flow rate remained the same, 96 meter cubic per hour. The difference is in temperatures, in delta T. So this is why the infrastructure remained the same subsystem. And when we go on the facility level, the flow rate also remained the same, but the capacity can be from 45 megawatt to 162 megawatt. The difference, again, is temperatures, delta T. But however, we always deliver that in the right place and in the best conditions. So, of course, there was many challenges which we already solved. I will not mention all of them. It's not enough time. However, I want to highlight about the CapEx. So if we look for the CapEx from point of view of cost per 1 IT kilowatt, so usually it is normal, traditional data center, it is 10 million euros per 1 megawatt, so roughly it's 10,000 euros per kilowatt. In our case, we reduce that till 2,000. And this is not magic, it's just advanced solutions. However, it's a huge. And also that also represent like an embedded carbon, because always when we will evaluate the carbon emissions, it's connected with the costs. The conclusions and takeaways. So this modular open source data center design allow to hyperscalers unlock the possibilities to go to the heart of the city in Europe and solve environmental challenges, social challenges, and financial. All these three pillars are solved in that solution. So we allow to make heat reuse, we provide the safety, modular standardization, which allow you to go everywhere globally. It's reduced a lot of times and cost with the designing works. And also you can have flexible modules. It can be 1,000 rack, 3,500 rack, 5,500 rack. Depends from the diameter of the cave. And of course, we can achieve really high temperatures without using the heat pumps. And call to action is to work with data center facility sustainability workstream and also introduce that solution for the cooling environments in OCP. And of course, if you want to learn more, you are welcome and we can help you more. Thank you for your attention.
Thank you so much. We have time for maybe one question. Anybody?
What are the downsides?
The downside.
Please.
The downside is you need to go underground. So because we have it's not a situation where you can have anybody just enter and leave as they want any day, any time of the day. It's a secured environment, so there are certain rules to follow. So it's not like a building where you could sort of just have in and out by many people. Here you have a number of people has to be restricted, and there's a safety considerations.
Take one more quick one here.
Thanks. This is great news for me because I've got an underground car park for sale in Helsinki to turn into a data centre. So you've just given me a great promotion on that. But there are many, many facilities, redundant facilities already available, such as the ex-NATO buildings, and underground car parks and things like that. Maybe we should look at those first before we start burrowing underground, because in somewhere like London, the complexities of building a new underground data center would be extreme in terms of avoiding existing services.
You want to answer that?
Yes, so of course, we provide open source solution. It means that it can be applied for existing underground spaces, but at the same time, what we show that the price of the underground data center it's relatively much lower. That it makes sense to even build new one in exactly where you need to make heat use, because maybe your existing building is far away from the district heating networks or from the customer. But both options is possible. And thank you for the question.